Objective 3, we want to convert from rectangular coordinates to polar coordinates. So now we're going in the opposite direction. So converting from rectangular coordinates to polar coordinates is going to be a bit more complicated than going from polar coordinates to rectangular coordinates. So for our theorem here, for converting rectangular coordinates to polar coordinates, we have that if P is a point with rectangular coordinates, x, y, the polar coordinates are theta of P are going to be given by r squared is equal to x squared plus y squared, which then we get the tangent of theta is equal to y over x if x is not equal to 0. Then we have that if x is equal to 0, we get that r is equal to y and theta is just pi over 2. That would be when theta was pi over 2, is that's when x is equal to 0. So to use these equations effectively, we have to follow these 3 steps. Step 1, we just want to plot the point xy as shown in examples 5, 6, and 7 from your book. So you just want to plot the point xy on a normal rectangular graph. Step 2, if x is equal to 0 or if y is equal to 0, then we just use the graph to find r. If x is not equal to 0 or y is not equal to 0, then we know that r is equal to the square root of x squared plus y squared. Then step 3, to find theta, if x is equal to 0, y is equal to 0, we're going to use the graph to find theta. Then if x is not equal to 0 and y is not equal to 0, note that the quadrant in which the point lies. So we'll have to find where the point lies in our rectangular coordinate system. So finding out if it lies in quadrants 1 through 4, or which quadrant it lies in, and then according to which quadrant it lies in, if it's in quadrant 1 or 4, which is going to be when x is always positive, but y changes, we'll get that theta is equal to the tangent inverse of y over x. Then if it's in quadrant 2 or 3, where theta is, or where we see where x is negative and y is positive or negative, we get that theta is going to be equal to pi plus tangent inverse of y over x. So essentially we always want theta to end up being positive or have x values that are positive. So all right, we're going to use the steps here to do our example where we're going to find the polar coordinates of a point whose rectangular coordinates are -1, negative square root of 3. So all right. Our first step is that we want to plot the point x, y. So let's go ahead and draw this out. Oh, do not want to use that. And it's a little thin, but we'll work with it here. There we go, and fix it up. There we go. And now we'll draw another one. So now we have our plane, which is, this is our XY plane here. So we know that our x value is going to be -1. We'll state it's about here. This is -1. And this right here is going to be negative square root of 3. So our point is going to lie right about there, which means, so we'll put point -1, negative square root of 3. Which means that if we're following from the polar axis, we're going around in this direction, and we get that this is theta. Then remember we draw a ray going out this way, and we get that this value here is r. Our point is in quadrant 3. So this was step 1. Step 1. Step 2, we want to find r. We know that x or y are not equal to 0, so we know that r is going to be equal to x squared plus y squared. x squared in this case is going to be -1 squared, and y squared is going to be negative square root of 3 squared. The square of -1 is going to be 1, and the square of negative square root of 3 is 3. So we get r is equal to the square root of 1 plus 3, which is equal to the square root of 4, which is just 2. So r is equal to 2. So we found our value of r in step 2. Now for step 3, we're going to find theta. So for step 3, we know x and y are not equal to 0. So we find what coordinate it's in, which we already did. It's going to be in quadrant 3. And since it's in quadrant 3, sorry about that. So we're going to find theta, where -1 comma negative square root of 3 is in quadrant 3. Since it's in quadrant 3, this means that theta is equal to pi plus tangent inverse of y over x. So we get theta is equal to pi plus tangent inverse of negative square root of 3 divided by -1. This simplifies down to tangent inverse of just square root 3, since we see negative square root of 3 divided by -1. We're really just getting rid of the negative there. So this is going to become tangent inverse of the square root of 3. You can use a unit circle to find this value. You can also use a calculator. But we see the tangent inverse of the square root of 3 is actually going to be equal to pi over 3. Then all we need to do is add pi over 3 to pi, which then is going to give us 4 pi over 3. So now we have our value of r and we have our value of theta. So now we can say, thus the polar coordinates for the point -1 comma negative square root of 3 is going to be 2 comma 4 pi over 3. I realized I wrote poorly. All right. One last note here, if you are asked to find other variations of the polar coordinate, remember you are either adding or subtracting 2 pi k from your value of theta. So some other answers could end up being something like -2 pi over 3 or 2 comma -2 pi over 3. So just remember, this was from objective 1, where we just established that there are multiple different coordinate or polar coordinates for a single, for any single polar coordinate. There's infinitely many equivalent values. So these would just be more equivalent values there. And they were found just using that, that definition that we had for those other polar coordinate systems back from objective 1 in this section. So, all right, our last objective here, we have objective 4. We're going to transform equations between polar and rectangular forms. So equations 1 and 2, which if we remember, these are equations 2. This here is equation 1. So our conversions, these are the equations that we're talking about. So our conversion equations can be used to transform one form to another. The common techniques for this would be to either multiply both sides of the equation by r or square both sides of the equation. And we'll see both of these techniques here in a moment. So example 5, we want to transform r is equal to 8 times cosine of theta from polar coordinates to rectangular coordinates. And then we want to identify the type of graph that we're drawing out. So what we're given here is we're given our polar coordinates. So we're going from polar coordinates to rectangular coordinates. So what we can do is we're going to multiply each side of this equation by r. So let's multiply each side of our equation by r. In order to use equations 1 and 2. So if we do this, if we multiply each side of our equations by r, we're going to get r squared is equal to 8r cosine theta, which r squared is just equal to x squared plus y squared, which we got from equation 2. So this is going to turn into x squared plus y squared is equal to 8r cosine theta. Now we can also identify that from equation 1, so from equation 1, x is equal to r times cosine theta. So this again is going to now turn into x squared plus y squared is equal to 8x. So now we've taken this equation which had r's and thetas, and we've now rewritten it so that it's only in terms of x and y. So we can say now we have an equation in terms of only x and y. So we're in our rectangular form. The other part of this question was that we want to identify the graph. What we have here is x squared plus y squared is equal to 8 squared. Anytime you really are going to have x squared plus y squared is equal to some value, you have the equation of a circle. So we have the equation of a circle. So let's go ahead and put this in standard form. So we're just going to rewrite it. In standard form. So the answer we got there, that's in rectangular form. Now we're just simplifying down since we've identified that this is the equation of a circle. So our graph is a circle. But so what we can do is we're going to complete the square. So if we want to complete the square, this means that we're going to rewrite our equation as x squared minus 8x plus y squared is equal to 0. So we complete the square. Remember, if we complete the square, this means that we want to find the values of x plus or minus some value squared. We want to replace that with what our value of x squared minus 8x is going to be. So if we want to rewrite this as a polynomial, we need to find that third term of our polynomial. And then whether we add or subtract it, we will then add or subtract to both sides. Hint, since it's a square, it's always going to be addition. So whatever value you add on in order to complete your square, you have to add to both sides. So to complete the square, what we're going to end up doing is we'll add 16. And we have to add 16 to both sides. So now we have x squared minus 8x plus 16 plus y squared is equal to 16. Now, x squared minus 8x plus 16 simplifies down to just x minus 4 squared plus y squared is equal to 16. And this looks a lot more like the standard form of the equation of a circle, which we see here. If we want to think about the equation of a circle, we have our radius of our circle equaling to 4. We see, the value of x is displaced by 4 values, things like that. So we have our standard form here. So we say this is the standard form of the equation of a circle with our center at 4, 0 and a radius of 4. So what our question asks was that we wanted to transform our polar coordinates to rectangular coordinates. So we did that by replacing all of our r's and thetas with x's and y's. So that was our first answer of x squared plus y squared is equal to 8x. Then we wanted to identify the graph. So identifying the graph was rewriting that equation, finding the equation of the circle, and rewriting that in standard form. All right, so our last problem here, example 6, now we're going to transform from a rectangular coordinates to polar coordinates. So for example 6, we want to transform 4xy is equal to 9 from rectangular coordinates to polar coordinates. If we want to transform these, we're actually just going to use the conversions from equation 1 to replace x and y. So we're going to use equation 1 to replace x with r is equal to cosine of theta and y is equal to r sine of theta. If we did this, this means that we'll end up getting 4 times r cosine theta times r sine of theta, which is equal to 9. Then if we combine these, we can just rewrite this as a 4r squared times cosine theta times sine of theta, which is equal to 9. So what we have here is that we no longer have x's and y's, we only have r's and thetas. So this value here, this is now the polar form. So this is the polar form. It's the polar form because we've replaced x and y with r's and thetas. As soon as you do that, that means that you are already in the polar form. Now what we can do is try and simplify. So we can now try to simplify our polar equation. There's really just one more step that we're going to do. We're going to factor 4 into 2 times 2. And when we do, we can write this now as 2 times r squared times 2 times cosine theta times sine of theta, which is equaling to 9. And all we did here was we were replacing 2 times cosine of theta times sine of theta. This, if you recognize, is the double angle formula. For sine. So really we just identified something that we could have replaced and replaced it. So now we have 2r squared times sine of 2 theta is equal to 9. So this is technically our most simplified polar form. So let's just make a note of what we had here. So once you replace x and y with r and theta, it is now considered to be in polar form. So once you have it in polar form, you're just going to simplify. Same thing goes with the other direction. If you're going from polar coordinates to rectangular coordinates, it is in the different form as soon as you don't have whatever values that correspond to that form. So in this case, when we had 4xy is equal to 9, as soon as we replaced x and y's with r's and theta, it's now in polar form. We just simplified. Same thing for our last problem. We started with r and theta. Once we replaced r and theta with x and y, that was then in rectangular form, and you just want to simplify as much as possible or put it into a better form, like using our standard form with the equation of a circle. When running into questions like these on MyMathLab, it's going to be really important to look at what they want. So if it says, put your answer in standard form, put your answer in its most simplified form, this is really what you're going to be looking out for. You want to see if you can simplify it down into one of these forms as much as possible. So all right, that wraps up section 9.1. So I'll see you all again in section 9.2.